So, we begin Chapter 9, Counting and Probability. Helped if I turned it on. Introduction to Probability. Imagine tossing two coins and observing whether 0, 1, or 2 heads are obtained. It would be natural to guess that each of these events occurs about 1/3 of the time, but in fact this is not the case. Table here shows actual data obtained from tossing 2 quarters 50 times. You can see that one head happening occurs approximately twice as many times as the other two. Formalize this analysis and extend it to more complex situations. We introduce the notions of random process, sample space, event, and probability. To say that a process is random means that when it takes place, one outcome from some set of outcomes is sure to occur, but it is impossible to predict with certainty which outcome that will be. For instance, if an ordinary person performs the experiment of tossing an ordinary coin in the air and allowing it to fall flat on the ground, it can be predicted with certainty that the coin will land either heads up or tails up. But it is not known for sure whether the heads or tails will occur. We restrict this experiment to ordinary people because a skilled magician can toss a coin in a way that appears random, but is not. And theoretically, it's possible for a physicist equipped with first-rate measuring devices to be able to analyze all the forces on a coin and correctly predict its landing position. Just a few of many examples of random processes or experiments are choosing winners in state lotteries, selecting respondents in public opinion polls, and choosing subjects to receive treatments or serve as controls in medical experiments. The set of outcomes that can result from a random process or experiment is called a sample space. A sample space is a set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. In the case of where the experiment has finitely many outcomes and all outcomes are equally likely to occur, the probability of an event is just the ratio of the number of outcomes in the event to the total number of possible outcomes. So the equally likely probability formula: if S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, denoted by P of E, is equal to the number of outcomes in E to the total number of possible outcomes in S. For a finite set, then N of A denotes the number of elements in A. With this notation, the equally likely probability formula becomes P of E equals N of E over N of S. An ordinary deck of cards contains 52 cards divided into 4 suits: diamonds, hearts, black suits, clubs, and spades. Each suit contains 13 cards of the following denominations: 2 through 10, Jack, Queen, King, and Ace. The cards Jack, Queen, and King are called face cards. A couple of mathematicians working in 86 and 92 showed that 7 shuffles are needed to thoroughly mix up the cards in an ordinary deck. In 2000, a mathematician and his father, a mechanical engineer, used a somewhat different definition of thoroughly mixed up to show that 6 shuffles are nearly always sufficient. Imagine that the cards in the deck have become, by some method, so thoroughly mixed up that if you spread them out face down and pick one at random, you're as likely to get any one card as any other. What is the sample space of outcomes? What are all the possible, how many possible outcomes are there? What is the event that the chosen card is a black face card? What is the probability that the chosen card is a black face card? Well, the number of possible outcomes in the sample space S is 52, because there are 52 cards in the deck. Let E be the event that a black face card is chosen. The outcomes in E are the Jack, Queen, and King of clubs and spades. So by part B, N of E equals 6. According to the description of the situation, all 52 outcomes in the sample space are equally likely. Therefore, by the equally likely probability formula, the probability that the chosen card is a black face card is 6 divided by 52, or approximately 11.5%. Counting the lists of elements of a list. Some counting problems are as simple as counting the elements of a list. For instance, how many integers are there from 5 through 12? To answer this question, imagine going along the list of integers from 5 to 12, counting each one in turn. You get something like what's shown here, giving the answer to be 8. More generally, if m and n are integers and m is less than or equal to n, how many integers are there from m through n? To answer this question, note that n equals m plus n minus m, where n minus m is greater than or equal to 0. Note also that the element m plus 0 is the first element of the list, m plus 1 is the second element, and m plus 2 is the third, and so forth. In general, the element m plus I is the ith plus 1, or the ith plus 1 element of the list. Yeah. So the number of elements in the list is n minus m plus 1. So the number of elements in a list theorem, if m and n are integers and m is less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. How many 3-digit integers from 100 to 999 are divisible by 5? What is the probability that a randomly chosen 3-digit integer is divisible by 5? Well, imagine writing the 3-digit integers in a row, noting that those are multiples of 5, and drawing arrows between each such integer and the corresponding multiple of 5. It is clear from this sketch here that there are as many 3-digit integers that are multiples of 5 as there are integers from 20 to 199 inclusive. So, by theorem 911, there are 180 such integers. Since there are 180 3-digit integers that are divisible by 5. By theorem 911, the total number of integers from 100 to 999 is 900. By part B, or part A, 180 of those are divisible by 5. Hence, the probability that a randomly chosen 3-digit integer is divisible by 5 is 180 divided by 900, or 1/5. Analysis of many computer algorithms requires skill at counting the elements of a one-dimensional array. Let A sub 1 to n be a one-dimensional array where n is a positive integer. Suppose the array is cut in at a middle value, m, so that two subarrays are formed, a sub 1 through a sub m and a sub m plus 1 through a sub n. How many elements does each subarray have? And what is the probability that a randomly chosen element of the array has an even subscript? Well, array 1 has the same number of elements as the list of integers from 1 through m. So by the theorem 911, it has m elements. Array 2 has the same number of elements as the list of integers from m plus 1 through n. So it would be n minus m plus 1 plus 1. So it restates the number of elements in a list theorem here. Now, for B, if n is even, each even subscript starting with 2 and ending with n can be matched up with an integer from 1 to n over 2. So there are n over 2 element arrays with array elements with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is 1 over 2. If n is odd, however, then the greatest even subscript of the array is n minus 1. So there are as many even subscripts between 1 and n as there are from 2 through n minus 1. Then the reasoning of I can be used to conclude that there are n minus 1 over 2 array elements with even subscripts. Since the entire array has n elements, the probability the randomly chosen element has an even subscript is n minus 1 over 2n. Observe that as n gets larger and larger, this probability gets closer and closer to 1/2. Note that the answers in 1 and 2 can be combined using floor notation. By fifth theorem 462, the number of array elements with even subscripts is the floor of n over 2. So the probability that a randomly chosen element has an even subscript is the floor of n over 2 over n. And that'll be it for that section. Come on now, cooperate. All right. Possibility trees and the multiplication rule. A tree structure is a useful tool for keeping systematic track of all possibilities in a situation in which events happen in order. The following example shows how to use such a structure to count the number of different ways a tournament can conclude. Teams A and B are to play each other repeatedly until one wins 2 games in a row, or a total of 3 games. One way in which this tournament can be played is for A to win the first game, B to win the second game, and A to win the third and fourth games, denoted by this here. How many ways can the tournament be played? Assuming that all the ways of playing the tournament are equally likely, what is the probability that 5 games are needed to determine the tournament winner? The possible ways for the tournament to be played are represented by the distinct paths from the root to a leaf in the tree, shown sideways in this figure. The label on each branching point indicates the winner of the game, and the notations in parentheses indicate the winner of the tournament. The fact that there are 10 paths from the root of the tree to its leaves shows that there are 10 possible ways for the tournament to be played, and they're given here. In 5 cases, A wins, and the other 5, B wins. The least number of games that must be played to determine a winner is 2, and the most that it will need to be played is 5. Since all the possible ways of playing the tournament listed in Part A are assumed to be equally likely, and the list shows that 5 games are needed in 4 different cases, the probability that 5 games are needed is 4 out of 10, or 4 out of the total number of possible outcomes, which is also equivalent to 2 over 5, or 40%. The multiplication rule. Consider the following example. Suppose a computer installation has 4 input-output units and 3 CPUs. Any input and output unit can be paired with any CPU. How many different ways are there to pair an input-output unit with a CPU? To answer this question, imagine the pairing of the 2 types of units as a 2-step process. Step 1, choose the input-output unit. Step 2, choose the central processing unit. And the possible outcomes of this operation are illustrated here. And you can see easily that there are 12 possible outcomes, or 12 possible pairings. The topmost path from root to leaf indicates that the input-output unit A is to be paired with central processing unit X, and so on and so forth. Thus, the total number of ways to pair the 2 types of units is the same as the number of branches of the tree, which is 12, or 4 times 3. The idea behind this example can be used to prove the following rule. The formal proof uses mathematical induction and is left to the exercises. If an operation consists of k steps and the first step can be performed in n sub 1 ways, and the second step can be performed in n sub 2 ways, and the kth step can be performed in n sub k ways, then the entire operation can be performed in n sub 1 times n sub 2, etc., to n sub k different ways. Multiply it all out. A certain personal identification number is required to be a sequence of any 4 symbols chosen from the 26 uppercase letters of the alphabet and the 10 digits. How many different pins are possible if repetition of symbols is allowed? How many different pins are possible if repetition of symbols is not allowed? What is the probability that a pin does not have a repeated symbol, assuming that all pins are equally likely? Well, some possible pins are given here. And you can think of forming a pin as a 4-step operation where each step involves placing a symbol into one of 4 positions, as shown here. Step 1, choose the symbol for position 1. Step 2, choose the symbol for position 2, and so forth. There is a fixed number of ways to perform each step, namely 36, regardless of how preceding steps were performed. So that by the multiplication rule, there are 36 to the 4th power pins in all, or 1.68 million, approximately. Part B. Again, think of forming a pin as a 4-step operation. Choose the first symbol, then the second, then the third, and then the fourth. There are 36 ways to choose the first symbol. And if you're not repeating, there's only 35 ways to choose the second, because you can't use the first symbol. And since you can't use the first 2 symbols, 34 on the 3rd step and 33 on the 4th step. Thus, the multiplication rule can be applied to conclude that there are 36 times 35 times 34 times 33, or 1.4 million different pins with no repeated symbol. So part C, there are 1.4 million pins with no repeated symbol, and there are 1.68 million pins in all. Thus, the probability that a pin has chosen at random contains no repeated symbols is approximately 84%, because it's 1.4 divided by 1.68. Consider the following nested loop. How many times does the do the statements in the inner body of the body of the inner loop execute? How many? Any ideas? The outer loop executes 4 times. The inner loop executes 3 times. So each execution of the outer loop, the inner loop executes 3 times. So 4 times 3 is 12. So it's the multiplication rule. The total number of iterations of the inner loop is 4 times 3, or 12. And you can see the trace table here would confirm that. So I iterates every, it goes up increments every 3 times j increments, and j gets reset each time I is reset, or is incremented. Permutations. A permutation is a set of a set of objects, is an ordering of the objects in a row. For example, the set of the elements A, B, and C has 6 permutations. In general, given a set of n objects, how many permutations does the set have? Do the multiplication rule, not repeating. How many do you have? You have, in the first element, you could be one of 3. Second element could be one of 2, because there's only 2 left that haven't been chosen. And then the last one, there's only going to be one left, because the first 2 haven't been chosen, or have already been chosen. So it would be 1 So how does that relate to n? Remember that function from chapter 5? Factorial. 1 times 2 times 3, etc., all the way up to n. Same type of thing going on here. Forming a permutation is an n-step process. Choose an element to write first, choose an element to write second, etc. Any element of the step can be chosen in step 1, so there's always n ways to perform that step. N minus 1 ways to perform step 2 because you can't choose the first one. So on and so forth. In general, the number of ways to perform each successive step is 1 less than the number of ways to perform the preceding step. At the point when the nth element is chosen, there is only 1 element left, so there's only 1 way to perform step n. Hence the multiplication rule. There are n times n minus 1 times n minus 2, etc., to 2 times 1, which is equal to n factorial ways to perform the entire operation. In other words, there are permutations of set n elements. There are n factorial permutations of a set of n elements. This reasoning is summarized in the following theorem. Again, a formal proof uses mathematical induction is left as an exercise. For any integer n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. How many ways can the letters in the word computer be arranged in a row? How many ways can the letters in the word computer be arranged if the letters CO must remain next to each other in order as a unit? If the letters of the word computer are randomly arranged in a row, what is the probability that the letters C and O remain next to each other as a unit? All 8 letters in the word computer are distinct, so the number of ways in which they can arrange the letters equals the number of permutations of a set of 8 elements. This is equal to 8 factorial, or a little over 40,000. If the letter group CO is treated as a unit, then there are effectively only 7 objects that are able to be arranged in a row. Hence, there are as many ways to write the letters as there are permutations of a set of 7 elements, or 7 factorial, for a little over 5,000. When the letters are arranged randomly in a row, the total number of arrangements and the number of arrangements with the letter CO next to each other, the probability is approximately, is 1 over 8, or 12.5%. Permutations of selected elements. Given the set ABC, there are 6 ways to select 2 letters from the set and write them in order. Each such ordering of 2 elements of A, B, and C is called the 2 permutation of A, B, and C. So the definition, an R permutation of a set of n elements, is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n elements is denoted by permutation the P of n and R. Theorem 923. If n and r are integers, and r is less than or equal to n, but greater than or equal to 1, then the number of r permutations of a set of n elements is given by the formula n factorial over n minus r factorial. So evaluate P of 5 and 2. How many 4 permutations are there of a set of 7 objects? How many 5 permutations are there of a set of 5 objects? Well, 5 of 2 is 5 factorial over 5 minus 2 factorial, or 5 times 4 times 3 factorial over 3 factorial, 20. Number of 4 permutations of a set of 7 objects, 7 factorial over 7 minus 4 factorial, or 7 times 6 times 5 times 4 times 3 factorial over 3 factorial, and that equals 840. Number of 5 permutations of a set of 5 objects is 5 factorial, because you're using all of the objects. Yeah. Don't forget the definition of 0 factorial is 1. Oh. And last up for the day, section 3. Counting elements of disjoint sets, the addition rule. In this section, we look at counting problems that can be solved by counting the number of elements in the union of 2 sets, the difference of 2 sets, or the intersection of 2 sets. The basic rule underlying the calculation of the number of elements in a union or difference or intersection is the addition rule. The rule states that the number of elements in a union of mutually disjoint finite sets equals the sum of the number of elements in each of the component sets. Just kind of common sense. 2 sets that don't have any elements in common, the total number is the number of each set. Common sense. How many 3-digit integers from 100 to 99 or 999 are divisible by 5? Well, the solution of the problem gives the addition rule, or uses the addition rule. Integers that are divisible by 5 end in either 5 or 0. Thus, the set of all 3-digit integers that are divisible by 5 can be split into 2 mutually disjoint subsets, a sub 1 and a sub 2. 3-digit integers that end in 0 and 3-digit integers that end in 5. Now, there are as many 3-digit integers that end in 0 as there are possible choices for the leftmost and the middle digits, because the rightmost digit must be equal to 0. As illustrated below, there are 9 choices for the leftmost digit and 10 choices for the middle digit. Hence, n of a sub 1 is 9 times 10, or 90, by the multiplication rule. Similar reasoning shows that there are as many 3-digit integers that end in 5 as there are possible choices for the leftmost and middle digits, which are the same for the integers that end in 0. So n of a sub 2 equals 90, which leads us to the number of 3-digit integers that are divisible by 5 is equal to 180. The difference rule. An important consequence of the addition rule is the fact that if the number of elements in a set A and the number of elements and a subset B of A are both known, then the number of elements that are in A and not in B can be computed. So if A is a finite set and B is a subset of A, then n of A minus B equals n of A minus n of B. Kind of another common sense one. The difference rule is illustrated here. Difference rule holds for the following reason. If B is a subset of A, then the two sets B and A minus B have no elements in common, and the union of B and A minus B equals A. Hence, by the addition rule, n of B plus n of A minus B equals n of A. Subtracting n of B from both sides gives you the equation n of A minus B equals n of A minus n of B. Consider the personal identification numbers. Same criteria as before. There are 1.68 million pins, approximately, with repetition allowed, and 265,000 pins with no repeated symbol. How many pins contain at least one repeated symbol? If all pins are equally likely, what is the probability that a randomly chosen pin contains at least one repeated symbol? Let S be the set of all pins with repetition allowed. Let A be the set of pins with no repeated symbol. And let S minus A be the set of pins with at least one repeated symbol. By the difference rule, you get n of S minus n of A is 265 is almost 266,000. Hence, there are 266,000 pins that contain at least one repeated symbol. Solution 1 to B. Because there are 1.68 million pins in all, and 266,000 of these contain at least one repeated symbol. By the equally likely probability formula, the probability that a randomly chosen pin contains a repeated symbol is approximately 15.8%. Solution 2, method 2, is the P of A is the probability that a randomly chosen pin has no repeated symbol. And so P of S minus A is the probability that a randomly chosen pin has at least one repeated symbol. So P of S minus A equals N of S minus A over N of S. And by the difference rule, N of S, that equals N of S minus N of A over N of S. By the law of fractions, you get N of S over N of S minus N of A over N of S, which is equal to 1 minus P over of A, because of the definition of the probability in the equally likely case. 1 minus 0.842 is approximately equal to 0.158 or 15.8%, which is what we got with solution 1. The formula for the probability of the complement of an event. If S is a finite sample space and A is an event in S, the probability of the complement of A is the 1 minus the probability of A, where the complement of A is S minus A. A certain computer access password consists of 3 through 5 uppercase letters, chosen from 26 letters in the alphabet, with repetition allowed. How many different passwords are possible? How many different passwords have no repeated letter? How many different passwords have at least one repeated letter? If all passwords are equally likely, what is the probability that a randomly chosen password has at least one repeated letter? Yeah. Set of all passwords can be partitioned into 3 subsets consisting of passwords of lengths 3, 4, and 5, as shown here. By the addition rule, the total number of passwords equals the number with length 3 and the number with length 4 and length 5. Multiplication rule can be used to compute the number of passwords of each length. So the passwords of length 3 are 26 to the 3rd power. Length 4 is 26 to the 4th power. Length 5 is 26 to the 5th power. So the total number of passwords is 12,355,928. Doesn't make for very strong passwords if they're that short, because a computer can easily go through all 12 million combinations and find out which one is the right password. Constructing a password with length 3 with no repeated letter is a 3-step process. 26 choices for step 1, 25 for step 2, etc. Thus, there are 26 times 25 times 24 passwords with length 3 with no repeated letter. Similarly, there are 26 times 25 times 24 passwords with length 4 with no repeats, and 26 times 25 times 24 times 23 times 22 passwords with length 5 with no repeats, which gives you a total of 8,268,000 passwords with no repeated letter. The total number of passwords is 12.35 million, and by part B, 2.87 of these million of these passwords do not have a repeated letter. Thus, by the difference rule, the number of passwords with at least one repeated letter is 4,087,000 and change. Given the assumption that all passwords are equally likely, the equally likely probability formula can be used. So the probability that a randomly chosen password has at least one repeated letter is 4.0809 million divided by 12.36 million, or roughly 33.1%. The inclusion-exclusion rule. The addition rule says how many elements are in a union of sets if the sets are mutually disjoint. Now consider the question of how to determine the number of elements in a union of sets when some of the sets overlap. For simplicity, begin by looking at a union of 2 sets A and B, shown here. The inclusion-exclusion rule for 2 finite sets is the number of elements of A union B equals the number of elements of A plus the number of elements of B minus the number of elements in the intersection of A and B. So how many integers are there from 1 through 1,000 that are multiples of 3 or 5? How many integers from 1 through 1000 are neither multiples of 3 nor multiples of 5. Let A and B be the sets of all integers from 1 to 1000 that are multiples of 3, and the integers that are multiples of 5. Then A union B is the set of all integers that are multiples of 3 or 5. A intersect B is the set of all integers from 1 through 1000 that are multiples of both 3 and 5, which is equal to the set of all integers from 1 through 1000 that are multiples of 15. Because every integer, a third integer from 3 to 999 is a multiple of 3, each of them can be represented in the form of 3k for some integer k 1 through 333. Hence, there are 333 multiples of 3 from 1 to 1000. Similarly, each multiple of 5 from 1 through 1000 has a form of 5k for some integer k from 1 through 200. There are 200 multiples of 5 from 1 through 1000. N of b equals 200. Finally, each multiple of 15 from 1 through 1000 has a form of 15k for some integer k from 1 through 66. Hence, there are 66 multiples of 15 from 1 through 1000. And n of a intersect b is equal to 66. Now, just ignore the typo here. It follows by the inclusion and exclusion rule that the union of the number of elements in the union of A and B equals the n of A plus n of B minus, not plus, a little flaw in the slides here, minus n of A intersect B. Got it right on the second line, which is 33 plus 200 minus 66, which is equal to 467. Thus, 467 integers from 1 through 1000 are multiples of 3 or 5, 3 or 5. There are 1000 integers from 1 through 1000. 467 of these are multiples of 3 or 5. Thus, by the difference rule, there are 533 that are neither multiples of 3 nor multiples of 5. And that would be it. Easy day today. 3 sections, a little less than an hour. And counting is getting a little bit more formalized. Anyway, you still have until Thursday before class to complete Chapter 5's homework. I never did change the due date on that, so you can still work on those if you haven't finished them. But that'll be it for today. Have a good day, and I will see you on Thursday.